Hi class, for these type of problems, we're going to be looking at the Poisson distribution. Now, here are the main aspects of the Poisson distribution that I need you to take a look at before we evaluate any problem. So a Poisson, it's going to be defined over some sort of an interval. The interval could be time or area. So let me write it as time or area. And then also you're going to have that, well, the event occurs over some sort of an A to B. In this case, that's what it's referring to. And in any of those points A through B, which is the interval, the event could occur at any time, and any selection has the same chance of being selected. So you're just going to have some interval and the event occurs during that time. If you do have a Poisson event, then the following formulas need to be used. This is the most typical one, where we're going to be using mu equal to the number of successes divided by the interval. On other problems where the random variable happens to be a multiplication, there's going to be a lambda t. So that would be for multiplication. The wording may be per values within the interval. And once we know that we do have a Poisson event, then these are the formulas that we're going to be using. Some of these Poissons, notice this sketch here may be approximately bell-shaped. So you're still going to have the usual interval equaling technically mu minus 2 sigma and mu plus 2 sigma, since we're still looking at the empirical rule on some of these, which means that on the edges, you're not going to have a lot of values for the probabilities. Lastly, another aspect of this distribution that it's going to show up in this week is that, well, binomial distribution. So what you're going to see is that some Poissons are going to be bell-shaped, and some bell shapes you're going to be able to approximate it by the Poisson and the binomial. In this case, for the Poisson and the binomial, you're going to get a very good approximation on each of those if the following is true. So those are the requirements. And lastly, the code that we're going to be using for our evaluation, here's the following. If we're evaluating an exact value, in this case, the probability of some random variable equals, you're going to be using PDF. If it says greater or less than, we're going to have to adjust it to less than or equal, and the code is going to be the CDF. So less than or equal, CDF would be the proper code. Let's take a look at the first problem, and we're going to be using the actual formula, and then I'll show you the code. So in this case, they want us to evaluate x is equal to 1. Now notice the formula, it uses lambda. And one of the formulas that we have for lambda is equal to lambda t. Now, if t is not stated in a problem like this, we use the unit of 1. So in this case, use lambda equal to 1 and mu is equal to lambda t. We do have the mean, so this is 0.3 is equal to lambda times 1, which actually means that lambda is equal to 0.3. So in the formula, we're going to be using, the formula says lambda to the x is 1. So 0.3 to the first times e to the negative 0.3 divided by technically 1 factorial. 1 factorial is simply 1. So we're going to be punching into the calculator 0.3 times e to the negative 0.3. And this is in fact the exact value. From here, we're going to do a decimal approximation. So let me show you where to find the e. In this case, we need first the 0.3 times the e is in the ln button. So second and ln, and then negative 0.3. Close that. And we're going to get that evaluating this formula. We're going to get the approximate of 0.22. So we would simply say on this one, approximately 0.22. There's like 4 2s. 1, 2, 3, 4, yeah. Now, the easiest method of evaluation, it's going to be what I talked about earlier. If it's a specific value, you're going to be using the PDF, and it already has the code embedded. So this one will be second in distributions, and then you're going to find the PDF. The calculator uses mu, which in this case it'll be 0.3, comma 1. And what you're gonna see is, whoops. I picked the wrong one. So it's the Poisson PDF. 0.3 comma and then 1. Okay, there we go. So that's gonna give us the 0.22. And the code is mu and x's. So I put the code here. Let me just show it. So this is going to be the values of mu and then your x value. That's actually it for the first evaluation. I just wanted to do one with the formula. The rest of them will be using the code. Let me move on to B. And in B, they're using 0. And notice that we already declared the variable, so we don't need to declare it anymore. So for 0, and let me run the code, you're simply going to use the Poisson PDF 0.3 and then technically 0 successes. And I'm getting approximately 0.74. I also put the code here. So this one's going to give us approximately 0.74. There's a 0.8. I'll just keep it. So 0.74, 0.8. That's it for B. Let's take a look at C. Now, C is a little bit tricky because it has a less than. And the code, in this case, the most appropriate one will be the CDF. That one uses less than or equal. So for this one, since you technically have that we're using less than 3, this is going to represent the probability of x is equal to 0 plus the probability of x is equal to 1 plus the probability of x is equal to 2. Or you could also evaluate the probability of x is less than or equal to 2, but using the proper code, which in this case, it'll be the CDF. Now, let me show you this one. So it has the same inputs. CDF, it'll want the mu, and then technically, because it says less than 3, you're not including 3, you're just going to evaluate 2. And this one will give us 0.9964. I already put the code here. So this one's giving us approximately 0.9964. Once again, since the random variable is integers, less than 3 does not include 3. That means within the Poisson 0, 1, and 2, not 3, which is less than or equal to 2, which it'll just be the 0.64. Let's move on to one that's a little bit more tricky, and this is including D. Now, let me write out what D is asking. D is asking for greater than 2, which within the Poisson means x is equal to 3 plus the probability of x is equal to 4 plus the probability of x is equal to 5. And then technically this event goes on indefinitely. So what they're trying us to evaluate is all of these. This will represent the probability of x is greater than 2. This is x greater than 2. Now, because you're having a distribution, the sum of all of these, so this is the sum of p of x, they have to equal to 1. So in this case, it's just easier to evaluate the complement. And the way to evaluate the complement is by evaluating 1 minus the probability of x is less than or equal to 2. So if you subtract from 1 all of these, you're going to get the rest, which is 3, 4, 5, what the event is actually using. As I mentioned, it's a little bit confusing because if you were to subtract technically from 1, the purple ones, which is less than or equal to 2, that's going to give us what we're looking for. And notice that you cannot evaluate it directly because n is not given. This n value, we just know it's a very large value, it's not stated. So in this case, we would have to adjust it with the complement. So we would be doing another CDF. Actually, we already did it. It's the one above it, which is going to give us, so in this case, this is equal to 1 minus less than or equal to 2 was 0.9964. And this is approximately 0.0036. Let me double check that. 3 and 2. Yep, that's actually it. Once again, statements that are expressed as greater, we always have to rewrite them as, in this case, well, less than or equal with the CDF. Also, your calculator, it may actually evaluate for you greater than 2. So you would see that when you type in the CDF, you may have that key. Most of us won't have it. I don't have it on the emulator. That's actually it for problem D.